It's easy to understand water has a temperature to tell us how cold or hot it is. It's easy to understand water has a salinity to tell us straight up how much salt it has. But what about water having a pH, telling us how acidic or basic it is? What does this mean? Whether you're studying chemistry or just want to learn more about water as a valuable resource, pH might get confusing. Let me try to explain. pH is a property of water or anything containing water. Foods, drinks, cosmetics, cleaning products, and even our blood. Here's the deal. If we could look closely at the water molecules in any of these examples, we'd see that not all of them are as H2O. If we start searching, we'd find that some of these molecules seem incomplete. Every now and then, we should see a hydrogen ion, all by itself. And further out in our search, a hydroxide ion. Why is that? This is because very rarely, two water molecules get close enough to each other, and the position is just right that a hydrogen ion leaves the molecule in pursuit of another. If we freeze this moment, you see that this leaves us with two ions in the water, H and OH, positive and negative. This will happen in any substance with water. Only a small fraction of water molecules do this. Maybe we find a pair of these ions for every 500 billion molecules. But remember, the number of molecules, even in a tiny drop, is far beyond any number I'm comfortable mentioning. So at the end, the presence of these very interactive ions matters, and pH is a way to measure them. If these ions are found in equal numbers, it means their charges are balanced. It's a neutral state. Whatever this liquid is, it has a pH of 7. We can lose this balance in two ways. One possibility is that the hydrogen ion becomes more and more abundant. And the more this happens, the hydroxide ion seems to nearly disappear. We say the liquid has become more acidic. And the more acidic it is, the smaller its pH value will be, which can go all the way down to 0. The opposite can happen. The hydroxide ion can grow and grow in numbers, and as this happens, the hydrogen ions go nearly extinct. We say this liquid is more basic. Some people say alkaline. And this is represented by a larger pH value, which can reach all the way up to about 14. This is known as the pH scale, summarizing all possible combinations for these ions using these 15 numbers and any number in between. These pH values are easier to digest than the actual number of ions per liter and the dramatic changes these numbers can undergo. It's called pH because technically it is a formula that focuses only on the number of hydrogen ions. These long numbers are plugged into a logarithmic formula called P to give us the pH values we all know. We like a pH close to 7 because it's normally harmless and fit for life. We can tolerate different pH values to some degree, but we have to be careful, especially with strong acids and bases. Purified water with a pH of 7 means its ions are balanced, both found in relatively small numbers. Carbonating this water with CO2 makes its pH lower, of about 3.5. This means that somehow there are far more hydrogen ions present now. If we take some seawater, we will see it has a higher pH of around 8.2. This means fewer hydrogen ions and quite more hydroxide ions. There are many processes that can shift the pH by manipulating these ions. We just saw how adding CO2 brings the pH down. This is happening at a different scale with the CO2 we produce, entering the ocean and therefore also bringing the ocean's pH down. We will look at this in more detail, but for now, let's recap. Any liquid containing water will always have a small fraction of molecules dissociated into hydrogen and hydroxide ions. There is a wide scale of possibilities for these two ions. pH is a clever way to express where we are in the scale, by measuring the hydrogen ions and giving us a simple number. But beware, a small change in pH means a lot at a molecular scale.